Hello and welcome to part 3 of the video series Deep Learning with PyTorch. In this particular part, we are going to actually build a convolutional neural network on CIFAR10 dataset. In previous part of this video, we built the same kind of model but with a plain neural network. In this particular part, we are going to actually implement the CIFAR10 classification for CIFAR10 dataset using a convolutional neural network in PyTorch. Again, the goal of this video is not to build a classifier that is much more accurate on CIFAR10 dataset. The goal basically is to come up with the understanding of the tools and the flow of PyTorch for building a convolutional neural network. So for example, after this video, if you want to implement a convolutional neural network on your data set, maybe a different neural network, convolutional neural network, this video will help you building multiple models with that model and stuff like so. So let's go to Jupyter Notebook and import certain packages that we really need. So import Torch, import from Torch Vision, import datasets, from Torch Vision import datasets, and from Torch Vision import transforms as well, transforms, and import torch.nn as nn. So these might be the packages that we might be needing for this particular example. So let's see the data directory where the data resides. Again, if the data is not already downloaded here, it will download here. If it is already there, like in my case, it is already there. But not a big deal. If data is not already there, the command I'm going to execute in PyTorch will actually download the data. So let's copy the path and write that path as root directory as R, the raw path, and that's our root directory. And let's download the data. Here we are going to actually download the data in a way that, for example, we really want to transform the data from 0 to 1, and we also want to deploy the data in terms of tensors rather than images. So let's training loader, training data as datasets dot CIFAR10, and here we give the path of root directory, and then we say, okay, is this a training batch or a validation batch? So training batch for now. Download equals true, which means if the data is not already there in this particular path, it will download from the internet as long as you have internet connection. And then we basically set this transform as transforms dot to tensor, and what this will do is this will basically convert the data to the tensor to the shape of the tensor that actually is needed by the neural network for PyTorch. So that's about the training data. So let's now build the validation data as well. So for validation data, let's use the letter V for validation. Here we have to set this training as false, and the rest of the story stays the true. Now, because this data is already there in the directory, so it does not download. If the data is not there, don't worry, it will download and place that in that directory. So after this, we actually have to build the loaders or the iterators for different batches. So let's use the batch training mode. So training loader, let's say, is torch.utils.data loader, and here we actually set the training data, and batch size, we actually set the batch size as whatever batch size you like. For example, maybe 64, 128, or 50 or something. I mean, anything. And do you really want to shuffle the inputs? If you really want to shuffle the inputs, set that as true. Now do the same for validation set, just to make the batches for mini batch gradient descent, which is more stable than ordinary stochastic gradient descent. So use this V for validation, and then you go for example, the validation loader, and that will build an iterator for you to iterate over different badges, which is required for training as well as for validation. Now, after that, what we really, now we have our training loader available, our validation loader available. Now what we really want is to define our model, basically. So if you, for example, see this, just to, for example, see this X and Y in T0, for example, and if you see the shape of X, you will be noticing this is 3, this is the number of channels, and 32 by 32, that's the size of the image. So what we really want to care about in building the convolutional neural network in PyTorch, we have to keep track of the dimensions. And the way it is implemented is the following. So for example, model equals nn.sequential. And here we go and build our model. So first layer, let's say nn.conv2d, conv2d. And we first have to set the number of channels of our input. So now the number of channels is 3. Then we have to set the total number of convolutional filters. How many filters do we really want? Let's say our filters is 16 filters. Now what is the kernel size? So kernel size, let's say I set the kernel size as 3, and we can set the paddings and strides as well, no problem. Here the output channels will be 16. So that these are the input channels and these are the output channels of this layer. After that, we have to apply a nonlinearity. So let's set the nonlinearity as ReLU. So ReLU nonlinearity. And we may apply a max pooling on top of that. So for example, max pool 2D. And here we have to set how much max pooling you really want to apply. Maybe you can set the strides and padding if you want, but let's go this way. So here the size of the input basically from 32 to 32, here the size goes to 8 by 8 because, 16 by 16 because original size was 32 by 32. We keep the padding as 1, and the output size for the convolutional layer stays 32 by 32. And then after nonlinearity, it stays 32 by 32 by 16, obviously because there are 16 channels, 16 filters. But after applying max pooling 2D without a stride and without a padding, the size here, exactly here, is 16 by 16 by 16 by 16 because it's the 16 filters. So the size shrinks from 32 to 32 to basically half. Next we apply, let's say, another convolutional layer, conv2d. And we set, let's say, the number of channels now we are receiving as 16. Let's say the number of channels we are producing here is, let's say, 8. And then we have to set the kernel size as, let's say the kernel size is 3. We set that, and let's say the padding is again 1. So after this particular layer, the result will be basically a 16 by 16 by 8. 16 by 16 because of the image size, and 8 because the total number of channels, the total number of new filters are 8. We again may want to set a nonlinearity activation function. Let's say ReLU. We are missing a comma here, ReLU. And now the result after this ReLU is 16 by 16 by 8. If we, for example, apply a max pooling here, n dot max pool without a stride and without padding, and let's say we set the size as 2, the size 16 by 16 will shrink to 8 by 8. So the result here of the tensor will be 8 by 8 by 8. So that's the tensor result. If, for example, we want to move on, we can move on, or maybe we want to flatten out our input here and build a fully connected layer here. So for example, n dot flatten. So that's the flattening. And next we may want to implement some dense layer, for example, this linear, but that linear input will receive what flattened input. So that input will be the total dimension of this tensor after this max pool 2D, which is 8 into 8 into 8. And let's say this, the output, the total number of units for this dense layer, let's say the total number of units are 20, let's say. And then we may apply a nonlinearity, let's say ReLU nonlinearity. And after this ReLU nonlinearity, let's have the final layer, which is again a dense layer, which takes the 20 inputs and generate the outputs as there are the total number of classes. So let's say this is our model. Later on, we will be applying a cross entropy loss, which actually, for which we do not need to apply a softmax layer or softmax activation for the final layer. So that's our model. If everything is going fine, that's our model. Next, we basically define the optimizer. So let's define the optimizer. Optimizer as torch.optim dot let's say stochastic gradient descent, let's say, and we set the model parameters, and let's say the learning rate is, let's say, 0.01. Let's say that's our learning rate. After that, if optimizer is fine, we have to set our loss function. So let's say the loss function, we set the loss function as cross entropy loss. Let's say cross entropy loss. Now all set, model is defined, optimizer parameter are given, loss function is defined. Now we are really ready to implement the backpropagation mini batch gradient descent for a different number of epochs. Let's say the number of epochs we set as 5, just for illustration. For each epoch in a range of number of epochs, let's go for let's iterate over the different batches. So for X, Y in training loader, the iterator, let's say Y hat is actually model X. That's our X, Y hat. And then let's compute the loss as loss function, which takes the Y hat and Y, that's our loss. And then we have to set the previous gradients to 0 if there are any. Optimizer dot 0 gradients. And after that, we actually apply a backward pass. So backward loss dot backward. So that is actually one step of backpropagation. And after that, we basically update our parameters. Optimizer dot step, which actually update all the parameters. And we may want to print the loss after every epoch. So that's the training. It will take some time because these convolution operations, they are basically expensive, time expensive. So it may take, the 5 epochs may take time. Although we should have more than 5 epochs, maybe 100 or more than that. But just for illustration, let's run it for 5 epochs. So it will give us loss, and maybe the loss maybe go down epoch by epoch, maybe fluctuate somewhere, but eventually it goes down as the number of epochs increase. So let's wait for it. Yeah, it is taking some time, but let's wait for it. So it should give by now it should give the loss for the very first epoch. Yeah, it is giving there. So now epoch by epoch it will be giving us loss. So these are the errors, or basically the losses for 5 epochs. As you can see, if we increase the number of epochs, the loss will actually gradually go down. So let's now write a validation script and see what is the validation accuracy for 10 classes. So the correct example so far, the total example we have seen so far, no gradients because we are validating with torch.no gradient. And in this, we basically let's iterate over our validation examples, validation batches in validation loader, and Y hat, let's say, is model X validation, And let's predict the value as just a single value, which is the maximum torch dot max y hat, for which value it is the maximum. Let's predict that. And then let's see how many correct we really have found, which is p equals to this. And then for that, basically we have sum. So that's the total correct ones for this one. And let's accumulate them for earlier as well. And how many total we have seen so far. So that is basically, let's accumulate those as well. So that is yv.shape 0 and step by step. So after this, after we have done with this, let's print for the accuracy. The accuracy is the total correct divided by the total we have seen. So that's the accuracy. So let's see what the accuracy turns out for this. Obviously the accuracy will not be very great because we have just a few epochs to run, and it is for 10 classes it is 42%. So that's the convolutional neural network in PyTorch. It's very simple and easy to manage. So I hope you liked our video series. Please press the like button and subscribe to our channel, and share this with your fellows. Hope to see you next time.